Professor Reuter at Outotec in Finland in the frame of quite an interesting European project that we had the chance to work at together. You can read his profile on the booklet you've been given. It's a long story. So basically, I would say that he was a professor at University of Delft, but then has plenty of honorary professionarships around the world. He's been working, as I said, when we met at Outotec, then he a couple of years ago left, and he's now director at Helmholtz Institute of Freiberg for Research Technologies. He's been talking about circular economy, which was the topic we've been discussing a lot together. Thank you.
Good morning, ladies and gentlemen. Thank you, Stefano. I still fondly think how we met at Lugano that one evening when we were discussing. It was about 1.5 years ago. At that time, we started talking, among others, about circular economy. The topic shown here is part of a lecture I gave earlier this year in the US, so you can download that there. In 20 minutes, I'd like just to give you a bit of a path of my simulation career that started about 35 years ago in South Africa in the mining and metallurgical industry, and how that's been going through that career up till now, where we've tried to model particulate systems. And specifically, this is the core of the message. How do you go about scrap? We've been speaking about products this morning. I usually think, how am I going to get those metals out again and close the loop? And that's basically the core of the message. So I've got basically 3 messages: circular economy. I'd also like to speak about circular economy engineering and like to fit that into this discussion today. And then also, above all, we engineers, we like simulating, we get very excited about this nice stuff we do, but ultimately we also have to communicate that to society to show what we do and help them also understand the complexity of what we are busy with. A bit of a history, just to show where we were many years ago. Quite interesting, when I started at Helmholtz about a year ago, coming from Outotec from many years in industry and then in Delft, there was a connection. That was what it looked like when somebody from Freiberg, who graduated there, actually started that operation, that metallurgical operation in Japan. And my connection independently of that, and I only found that out a couple of months ago when I spoke to the president of Kosaka of this link. I was involved in also the design and optimization of the right-hand furnace, where we used a whole host of simulation tools to do that. I cannot show them all, but hopefully you'll see some indication of what we are busy with. So this is the type of circular economy picture you see in policy documents. What we've seen today, where is the pointer? If you look at the picture, what we've been speaking about this morning is more on the top right-hand side, the design, the production, etc. But there's a whole host of other actors in this field as shown over here. I come from more the left-hand side, which is the raw materials, the recycling bit, and then specifically from the metallurgical extraction side, making the metals either from ore, concentrate, or from recyclates, and from then residues. The type of products that you're creating, we try to get back and sort of close the loop within the limits of physics, as was mentioned quite a few times this morning. But all these steps somehow create residual waste, which we then have to manage. And that's not so easy. We try to portray a message we can close the loop. But all of you guys in the audience will know that entropy obviously limits that. Often there's also discussion independently of the energy system, which is actually enveloping the picture I showed a moment ago. It also creates waste, but requires a vast number of technology elements that actually have to flow into it, and that we have to get back. So for me, a better picture would be the one that sort of combines these two together. And it's interesting how sometimes these two pictures are disjoint from each other, even in the policy discussion. So we're trying to tell the consumer, you can consume, we can take it all back and recycle it. That's not so true. So we have to be very careful how we, as engineers, also portray that and also take part in that discussion. What are the limits of recycling and what are the opportunities as well? You'll see the little blue arrow on the right-hand side showing the technology elements that flow into the energy systems and the exciting new technologies that are being developed. But we as process engineers have to take it back and recycle it once it's at its end of life. So you'll see at the center, in summary, I always try to remind even the policy people and all the people that are writing these circular economy papers, please take care of the second law as well, because all those steps are creating randomness, are creating entropy, and we have to manage that. And the only tools that we can really do that with is not an Excel spreadsheet, as was mentioned earlier this morning, but it's using simulators that work obviously on a thermodynamic basis and can quantify these aspects. And that's not so easy. As I said, it's nice and easy. We can apparently make billions by closing the loop, but people forget the second law. So what I've been involved in, and this is what I'll do the next half of the talk and make it concrete with a specific example to show to you this balance energy materials. Among others, one of my tasks was to also help and also manage the development of a tool. And as the mission statement of Outotec was sustainable technology and playing an integral part of closing the loop and also providing solutions to customers that are sustainable, we spent a lot of time adding certain functionality, among others, exergy analysis. We also had life cycle assessment into the flow sheet and to actually show that. And I'd like to spend some time with you on those aspects. For those of you that are not familiar with this, this is the type of field I've been confronted with since 35 years when I started on the gold industry in South Africa. The left-hand side, you'd see a typical gold mineral or copper, gold, lead type of minerals. They've got a couple of elements. If you look at the designer minerals, all the products that we've spoken about this morning, which have got many more than just 15 elements, many compounds, alloys, materials joined in a very complex way, you cannot not simulate and understand the particles that are created from the scrap or as a total mineral and flows through to a furnace to recover the metals. So you need the detail. And that is still being totally overlooked, even in policy discussions. And sometimes it's a bit of a lone fight, because as I say, I'm always being confronted by the Excel brigade. So what I've also been involved in, just to tie to your discussion today, yes, we've also been involved intimately with CFD, myself as well, trying to optimize furnaces, trying to understand how we can go from a scrap, a residue, and as it was also said, the multi-physics at the bottom of that lance flowing into a reactor to optimize that bit. And that's by no means easy to understand the chemical reactions, the mass and heat transfer, the mixing, the wear and tear of the materials all at 1400 degrees centigrade. So just to give you an indication, my type of world, it's not jet engines or it's pumps, it's this type of furnace, for instance, giving you a bit of the dimension and a bit of the flows through it, up to 1.5 million tons per annum. So trying to optimize this whole bit from product, the designer mineral, right down to the recovery of the metals and materials and the plastics, etc. from that is what this is all about from my perspective. Just to show to you, it's not just academic. Here's a plant being built to do just that. Just gives you a bit of an indication of scale. The 20 meters I mentioned a moment ago, that big pot, it's being built in Australia at the moment, which is actually doing this, integrating and processing multi-materials and trying to close the loop within a corporation. which I feel is at the moment the easiest way perhaps to do it. Having gutsy CEOs that are actually directing this and making it work with the right technology, but ultimately to do this you need good simulation tools to link things together. So my question that I'd like to answer in the last few sheets, and this is perhaps one that you've not perhaps thought about. If you take an old lamp, I've shown it's got a few materials, and I compare it with an LED type of lamp. What is the better one from energy and materials perspective and closing the loop perspective? And these are very low-hanging fruits that we can answer. But ultimately, to do that well, we need to integrate the simulation tools in a way that it can be done. And as I said, modeling particle systems of this complexity is not so easy. So ultimately, the question is, and I've got this element picture inside there that would say, if I would recover all the elements in that product, and not just in an Excel sheet, but taking into consideration the losses in the system, the mixtures, the alloys, ultimately the thermodynamics at the recovery at the furnace in the end. If it were looking like this, I would have all the metals recovered, and therefore have a closed loop, as it is, as the wish is. But let's see what it looks like. We have on the left-hand side a typical design of a product. We have the bill of materials. A lot of people that tell us, well, the bill of materials is so complex. Why the hell can you do this? But then the question I would pose is, can we link CAD, understand the mineralogy so that we can know what residues or scraps we create, and then be able to determine what technologies are required to recover that. And also the message in here requires, if the EU would like to do a circular economy, it does not only have to do scrap, but it has to have the metallurgical infrastructure there as well. And that, as you know, is sometimes under pressure. So without the metallurgy, and that's the subtitle of the talk, we cannot do this. So what do we need, and can we go from the design of a product right down to the recovery and understand what infrastructure will require, then we would be a very large step further. So those little pictures on the right-hand side are not just a little reactor, it's a whole flow sheet. This specifically flow sheet is the one I mentioned to you in Kosaka in Japan, where the furnace and then the refinery infrastructure in totality recovers as many as possible materials that flow into that system. And so we call that the geometallurgy of the urban mine. I started my career the geometallurgy of the geological mine, and we've migrated. But you may ask, is this not just simple, flow sheeting? No. One has to understand the particles in its complexity, as I said, and how they react in the system. So here, this is still my dream. We have CAD, we have simulation linked to that. We can recover, really calculate on a thermodynamic base what comes out. We've integrated LCA, and then we come to this final thing. Can we show this to the consumer? We call it the recycling index. And by the way, a colleague and I, we've been working on this for about 20 years. And we were sitting in Rome a couple of years or so ago. And this is where it originated, at the Colosseum. So it's got a bit of an Italian origin. And you'll see why that specific symbol in a moment. I'm taking 5 LED designs. Design A to E or 1 to 5. Now usually you think, well, this is simple stuff. If you take it apart by hand, and you've got a lot of money in your pocket to pay the hours to do that, you'll get all the little bits and pieces in the middle row. But if you really go to a commercial plant where you'd like to recycle that and actually create recyclates, you get something which is slightly more complex. Now I'm sure you'll understand that the Navier-Stokes equation won't explain this type of material. It's rather complex in its mineralogy, much more complex than geological ores. And to understand that and flow it through the system to make a calculation is therefore still open to a lot of work. Where we are at the moment is the position here. You all know the left-hand figure. You buy your equipment with the energy efficiency. As I said, the right-hand side became just in analogy to the two. Try to show that if I have a product, look at energy and materials at the same time. Right-hand side shows to you a band that goes very concrete from 0 to 100% recycling. And obviously I can load on top of it the life cycle assessment as well, but then simulation-based. Now look at the lamp. Let's get back to that. As you know, it's got a pretty low energy efficiency. However, if you look at the recycling, because of its relative simplicity, you can recover a fair bit of materials. Looking at LEDs, the opposite picture. A higher energy efficiency, but recyclability not so good. This is, therefore, the main message of this talk. How do we balance that? And I do believe using good simulation tools, which we are trying to further develop and have developed to a fair degree, is trying to bring those together. Bringing the element wheel to it, here's even a worse design. This is we call it design F rating of 10 to 20% recycling rate, really poor. But the reason for that is, and you can drill down right down to the element level, and even compound level if you wanted to. Ultimately, how much can you bring back into the cycle? And you can see very clearly, you have this wonderful light, but resource efficiency is not so good. Merging this together, in addition to the computer-aided engineering on top, and actually making such evaluations and conveying that to the societies of extreme importance. So I was just mentioning, I've got another 2 minutes, I think. This is my final sheet. And ultimately, this sort of summarizes briefly what I tried to show. I've migrated from the geological mine to the urban mine, but we're using the same particle-based models, going not just in a simplistic way, but in its full complexity of mineralogy. Taking that through the whole cycle. At the bottom, you'll see the furnaces. The metallurgy is really the basis of a circular economy, of a closing the loop type of environment. Not having it, talking of circular economy is just hot air. And ultimately, actually bringing this together and linking the product design with that metallurgy. In other words, linking the bottom to on the left-hand side is, as I said, still a dream. Somebody just told me the other day, look at this bill of materials of this relatively small product. It's a list of zillions of lines. How the hell are we ever going to manage that? But I said, well, if you don't dream, you won't get anywhere. And I know it's difficult, but at least I think this is the first time in such a community. Usually I speak to process metallurgists, where we also have our simulation interest groups. But hopefully we can bring these worlds together and really make that a possibility to really understand and convey to society what we are doing. I thank you for your attention.